Basically, today we welcome Till from Deutsche Telekom. And since 2020, Till is working as part of the Magenta Zuhause app in Deutsche Telekom. And he initially worked with Thread and then with Matter, which he has analyzed and then came up with a proof of concept how it can be integrated into the Magenta Zuhause architecture. And yeah, in this process, he realized that Web of Things would be a good abstraction, and we should actually make things more resource efficient and lightweight, in addition to becoming standardized as well. With this, I'm giving the floor to Till, where we will hear about the Matter and the Web of Things, so the beyond local connectivity, bridging Web of Things and Matter. So, Till, the floor is yours.
So then it's my turn. Welcome everyone to this week's meetup session today. As Ike said, about bridging Web of Things and Matter. First, another introduction from my side. My name is Till. I'm a dual student at Deutsche Telekom. Started working in the smart home domain in 2020, and since then I'm working on Thread and especially Matter. And now this topic I'm talking about today was also part of my bachelor thesis. But about the agenda, I first start with smart home at Deutsche Telekom, maybe giving some introduction into our architecture and also talking about the motivation, which was behind my idea with this topic. After that, I will give an introduction to Matter, basic stuff, but maybe not known about everyone, and it's needed to understand the further concept I will talk about after that. And in the end, I will give a short look at my implementation, which was like a proof of concept about this shown concept. First of all, the architecture. We are developing a smart home platform, and our scope was never to be mainly a manufacturer, but instead working with different manufacturers. And all of that led to an architecture where we had like a lot of data models from different devices, which are locally bridged to standardized local model, and after that abstracted to our cloud infrastructure where we are using Web of Things. And my idea behind it was, okay, why are we doing a two mapping process, first locally and then for the cloud infrastructure? So I came up with the idea, how would it be to directly map a data model to the Web of Things? And Matter was the best data model to start since it's very popular. Now, the basic stuff about Matter, introduction. First, generally, it's an open standard, so the source code is available in the GitHub. It's all a working group of the Connectivity Standard Alliance, so they are standardizing the specification. And Matter aims for a higher connectivity for IoT devices in a local domain. Even though they are using IPv6, the scope is just local. The Matter layer architecture looks like Matter is only specifying the application layer, and for a seamless integration into the current local home network, Matter uses well-known network protocols as shown here in this diagram. You probably will know all of these names. And on top of the different protocols used on the link and media layer, Matter forms a virtual network called Fabric. So Fabric is like this Matter network we are talking about, and there are also maybe more than one Fabric, but it's not important for the data model. The data model in general starts with, of course, the physical device, and the first abstraction layer of this physical device is a node. A node is an addressable element which has an IPv6 address, and a node can consist of more than one node. So in this case, I have shown here two nodes. And after the node, we have the next abstraction layer, which is an endpoint. An endpoint implements a device type, which is an encapsulation of functionality. And it's also the endpoint of the communication. So if you are talking with a meta device, you're always talking with a node and then an endpoint. You can maybe think about something like an IP address and a port. And in this case, you have a node and an endpoint. And yeah, after the endpoint, it contains cluster. These cluster are also specified by a cluster specification, and they are implementing the functionality. And all of this is also specified by some requirements from the device type. The meta device type represents functionality from a category and defines cluster requirements. These requirements are also needed for the certification process. So if you think of a smart plug, which is implementing the smart plug device type, in the certification process, the Connectivity Standard Alliance can make sure that the device supports all of the clusters, and with that, all of the interfaces which are specified. And device type have the scope endpoint or scope node. I will talk about that in a few slides. And in general, I have this sentence down there, which is a meta device type defines the clusters that an endpoint must implement, because everything is coming down to this fact that the device type just defines the cluster which you have to use. An example for a device type would be dimmable light. As shown down there in the table, we can see the cluster requirements. In this case, on-off level control. You can think about the functionality which is behind that, but just that you have an idea how this could look. The root node device type is a special device type which has the node scope. As I said, there is the scope endpoint and scope node. Both device types are implemented by an endpoint, so that's not the difference. The difference is that a device type which has the node scope is only implemented once per node. So also in this case, the endpoint 0 is always the root node, and every node has one root node. And this is implementing basic information. Clusters are like basic information or general commissioning clusters. So really, information like the manufacturer name, the serial number, and information you may be seeking for like that are implemented in the root node. And the root node also contains a list with every name or every endpoint, which is also implemented under the node. So the root node is like the entrance of a node. Meta cluster implements functionality. It is also specified by a cluster specification, and it concludes the characteristics like attribute, comment, and event, but also specified cluster response codes in some cases, and examples would be on-off, level control, color control, and door lock. And this has the advantage, for an example, the on-off cluster, which may be used by the smart plug device type and the dimmable light device type, and so on. So a cluster is reused by different device types and then referred that it can support this functionality. Summarizing with an example, you can see there on the picture we have a normal light bulb with an on-off functionality. How would you model this light bulb? First of all, of course, we have a node, which is the first element with an IPv6 address. And underneath, we have two endpoints, one implementing the root node, because the root node is always implemented in endpoint 0. And after that, the endpoint 1, which is the on-off light with the functionality the light bulb has. Down there, of course, we have the cluster requirements from the device type, which are implemented. just a few examples. As you can see, a cluster on-off for the functionality, and a general information cluster on the root node with informations like manufacturer, serial number. A little bit more complex is the endpoint composition functionality. This is a relation between endpoints. So an endpoint can refer to another endpoint with a given context. This leads to more complex device types and allows to be more adaptable for different use cases. An example for an composed device type is the refrigerator. As you can see in the table, the refrigerator contains of at least one temperature-controlled cabinet. You may think, okay, what is the advantage of that? But it's clear if you take a look at this one. There we can see we have endpoint 0, which contains a list of every endpoint which is under the node. And then we have endpoint 1, which is the refrigerator, and it contains a list of the endpoint 11 and endpoint 12. These are temperature-controlled cabinet. And by looking at the semantic tag, which is given here, we can see that there are different definitions or contexts of the temperature-controlled cabinet. So we have one refrigerator and one freezer. So it's separated zones of the refrigerator, and even another manufacturer may have a 0-degree zone or included wine cooler, whatever. It's able to module this with the data model using the refrigerator device type. So that's the advantage of this. But endpoint composition also allows things like meta bridging. So it's a functionality for non-meta devices which can be bridged into a meta fabric, allowing old hardware support or other network protocols. In this case, one physical device acts as a meta bridge with the device type aggregator, and the bridge in this case is then referring to other endpoints, and every bridge device is then mapped to one endpoint, which is under the node of the aggregator. And as you can see here, we have an aggregator in endpoint 1, which is referring to endpoint 11, endpoint 12, in this case, extended caller lights, and they are bridged meta devices. Also, you can see that endpoint 11, endpoint 12 have two device types, bridged node. So with the hint that the device type is bridged node, we can see, okay, this is a bridged device and it's not supporting meta native. The last thing I want to talk about is the meta access control. So meta is defining the access in three rights. So read, write, and invoke. For every characteristic, it's defined. So for the attribute, comment, and event. And besides that, we have privileges shown here: operate, manage, and administer. And these privileges and access rights also imply each other. So if you say, okay, we have a characteristic like a comment with the access right invoke, then we need an operate privilege to exit it. Next on, we come to the concept. So now I will talk about, okay, we heard about the characteristics from Meta, how it's moduled, but how can we abstract it to a thing description, to Web of Things? We start with creating a thing description in general. The first question is, okay, are we creating a thing description for a node, for an endpoint, for every cluster? I came up with the idea that the best way to do it is an abstraction for every endpoint. We are creating a thing description because this provides a good separation of the functionality. And we also have two other things which we have to think about. The first thing is that different endpoints of a node could implement the same device type. And if we then think of one thing description for every node, we would have naming problems and have to use a prefix, and it would also lead to confusing files because they are very long. And yeah, also bridged meta devices are with this concept in one thing description. So we have a separation like in the real world with different physical devices. An example again, for the on-off light, we have two endpoints, root node and on-off light. So we are creating two thing descriptions for the root node and for the on-off light. Like this leads to the loss of the belonging to a node. So when you have these two thing descriptions, you can't say that they are both from node 1, but I also have a solution for that coming up in a few slides. Because in general, the abstraction of the relations is an interesting topic. We heard about 3 types of relations. First thing is the root node, which is referring to every endpoint. Next is the aggregator, so the meta bridge, that is referring to their bridge devices. And last one is the composed device type relation, like the refrigerator, that is referring to the components. And all of them can be described in the links array of a thing description. The only thing which we have to choose is the relation type. Down there you can see the sentence from the specification. So link context has a relation type resource at link target. So we have to come up with a link relation that is matching for that. In general, in Meta, the relations are unilateral, but in Web of Things, we have to model them bilateral. Quite simple, because if we think of the root node, which is referring to every other endpoint, we can then go in this direction. But if we are in an endpoint 2, for an example, and we want to know the root node, we can't go back. In the case of the metadata model, we always know, okay, endpoint 0 is implementing the root node, but if the thing description have other locations and we can't go back, because of that, we have to model bilateral. From the root node to endpoint 1, I was using a context extension of the meta specification, and they are referring to the element of the parts list attribute. And in this case, we have the relation type, which is the part list attribute from meta. In combination with the root node, we then know, okay, this is a list which contains every endpoint of the node. In the other direction, we can't refer to an element of the meta specification. In this case, I took a look at the link relation from Jena, and I was going for the describe by relation, because I have the sentence right there, refers to a resource providing information about the link's context, which is exactly what the root node is doing. So this relation type is perfectly matching for this use case. Next is the aggregator, so the meta bridge, which is also referring to the bridge devices. In this case, same as the root node, we are going for a context extension of the meta specification and then referring to the parts list attribute. In combination with the device type, we then know, okay, this is a list of every bridge node of the aggregator. In the other direction, it was a little bit harder to find a link relation. Jena has no matching relation type, and we also can't refer to the meta specification. So I came up with a relation type like aggregator. So with that, we know that this bridged node has to have one aggregator, and this is the link that is referring to the resource. The relation of composed device type, we there have a simple composition, and there we can also use a link relation from Jena, collection and item. There was an example think with electric drive in the thing description specification, example 29 and 30. And yeah, this is exactly what this relation is. So we can use the link relation in this case. Conclusion of the meta relations are that we have to model them bilateral, and we are using the links array and using relation types as described in this table right here, where I have summarized what I talked about in the last minutes. The access control of meta can also be described, of course, when we are describing properties, we can make use of the read-only and write-only attribute. Besides that, I took a look at the OAuth 2 security scheme, and I thought of maybe defining a meta security scheme which defines scopes, and we can then use the scopes for the privileges which are defined by meta, and yeah, define them in the forms array. As you can see here in this example, we have an on-off toggle comment from meta, and we are using a scope or defining a scope for the privilege that is needed to invoke this action. Then we have now abstracted the general model of meta into a thing description. The last big part that is needed is the characteristic from the cluster. So we have attribute, comments, and events. Quite easy. Attributes will be abstracted to properties, comments to actions, and events will be events, same name. And in general, we can have the naming with a prefix of the cluster name, and after that, the name of the characteristic. We can make use of the additional response attribute of the thing description to define cluster-specific response codes. And as I said in the security case, we can define these scope for the privilege. The attribute abstraction, we use the read-only and write-only attribute. The observable attribute is always false, since meta is implementing a pull communication, and the operate attribute of the form has to be read property. Here's an example, a simple one, just that you have an example how this could look. We see there observable is false, read-only, write-only is set for the access that we have. We have here the first of all the cluster name, and then the in this case attribute name, and yeah, same goes for the comments. The synchronous attribute is always true because the calling is taking place synchronously. We can use the input field to describe the input we have to provide for invoking the action. The operate attribute is invoke action, and the idempotent attribute has to be chosen for every comment itself, depending on if it's idempotent. Here's another example. Looks a little bit like the attribute one. Events are a little bit harder. The only thing that is changing for every cluster is the data that is returned in the data field. Besides that, we have to model the event lifecycle of meta. We can describe that with the subscription, data response, and cancellation attribute. And in general, this leads to a really long description. Because of that, I have no example provided here. But the only attribute which is changing is the data attribute. Besides the general abstraction, we can also define the context with the type attribute. We can there make use of the XML specification of meta, and we can also define the description attribute in a human readable way. For that, we can copy the definition from the meta specification. Here's an example. We can see there that we have here the context extension of the XML specification of the cluster. And here we have the element ID of the matching comment in this case, because it's an action. And besides that, we have here in the description attribute in a human readable way the definition from the meta specification, which can be provided here and gives a little bit more information. The next thing I want to talk about is a protocol binding. So in the end, a protocol binding provides every information that we need to make a request in the specified protocol. In this case, I was looking at the command line tool of Meta, the chip tool, and I took a look at what information do we need, and I came up with this 4 information. We need the cluster name, the interaction affordance name or characteristic name, the node ID, and the endpoint ID. So these are the 4 information that we in every case need. And if we then take a look at an example of a read request with the chip tool, we can then translate it to an href attribute in a kind of URL format using first of all the meta prefix, and then in a little bit different order the information that are needed. This could be an href attribute of a form object and is providing all of the information we then need to make a request with the command line tool of Meta. Same goes for the invoke and the subscription. Only difference is there that we have parameters that are defined. In this case, I was going for an definition like that. So this could be a way to describe an href attribute with a Meta protocol. Last point of the concept is the use of thing models. So in general, I think as Meta is, in general, in construction kit, so Meta is providing specifications for clusters and for device types, but in the end, it is once defined and reused by a lot of devices. So we can make use of the thing model, TM submodel and TM extend function, as I said, for the cluster specification and device type, but also for the event life cycle and the status codes defined by Meta. And in general, I think a library of the Meta specification with a thing model, so a library of thing models that are describing the Meta specification can then be used to define every thing description. So would be good to use this functionality. That's the end of the concept. In the next topic, I want to talk about my implementation. It was kind of proof of concept of what I did in first implementation. I was using the Node Web of Things library with TypeScript. Maybe a few of you read my messages in the Discord when I had questions about the library. It was the first implementation of the concept, and I was focusing on the extended color light device type because I had to use one device type. It would be too much to implement more than that. And I also implemented a simple discovery where I was first stepping through every node, and then inside the node, I was stepping through the endpoint, taking a look at the implemented device type, checking if it's the device type that I implemented, the extended color light. And if it was an extended color light, I was creating a thing description for that. And in the end, I had a RESTful interface that I was able to call with the HTTP protocol, and yeah, we're able to read, invoke, and everything. I have a short demo video after the slide. The implementation was on top of the Telekom meta controller. So it's calling the interface from our implementation. Yeah, besides that, the implementation can be reused. It's in my GitHub profile. You can take a look at it and maybe get an idea what I did. You won't be able to use it because, as I said, I was using the Telekom meta controller, but yeah, it's easy to adapt if you have other implementation of the controller. Here I have a short demo video. I don't want to show the whole video. It was just to get an idea how it looks. As you can see there, I have a normal route and can do a GET request and getting a thing description. And this thing description contains here every characteristic with the with the cluster prefix and then the comment, I think, an attribute in this case. And I was also able to then, with this abstraction, invoke comments like toggle in this case here. Toggle the LED, and I think I'm also changing the brightness and also the color. So as you can see, it's a normal RESTful interface that I'm using. And yeah, that's the end of my presentation. I'm now open for questions. Thanks, everyone.